Hello, everybody. So let's take a look at the remaining portion of section 6.3. So hopefully last week you spent some time working through the first little bit of 6.3. Of course, we took a look at our standard or our normal distribution, which is our bell curve. So a quick recap, our mean, our median, and our mode, all in the middle of the standard curve. And as we move outwards, either to the left or the right, we get one standard deviation away, typically here on this diagram, and we get a corresponding amount of the curve underneath, or sorry, a specific amount of the area underneath the curve. So from the exact middle to one standard deviation away, that's 34.13% of the data is there. And then another standard deviation is 13.59, and then another is 2.14, etc., etc. Okay. And of course, we learned that the standard curve gets closer and closer and closer to the x-axis, but never truly touches it. Okay. So let's take a look now at the next part, and we're going to be talking about what we call the z-score. Okay. So the thing is, with the curves that we were seeing previously, like this guy right here, right? For example, well, actually, here let's go to the nursing question with the baby, right? So we were dealing specifically with values that the baby was sleeping for exactly 12 hours, exactly 14, exactly 8, exactly 10. But what happens if we needed to discuss something at like 15 hours or 14 and a half hours, right? Because if we look here, this diagram doesn't give us the percentage of the area for the values between one whole standard deviation at a time. It just tells us the exact whole number standard deviation. So what happens when we get values between those? That's what we're going to take a look at today. That's what the z-score is. Okay. So let's go and take a look here. So the way z-scores work is every single data point in a collection of data has a corresponding z-score, right? The z-score is always going to be a positive number if it's to the right, and the z of the mean, and the z-score is always going to have a negative number if it's to the left of the mean. Okay, so this is the important thing to understand: is every single point that we get, every single data value, it's going to have another value that's a z-score. Okay, each point has its own z-score. Okay, so that's what we have here. All right, so if we have a data point that's exactly equal to the mean, so let's say, I don't know, 10, whatever, it doesn't matter. Let's say 10 is the mean for this graph. 10 would have a z-score of 0. All right. If the standard deviation of this data, let's say it was 3, for example, that means one standard deviation away from 10 would be 13, right? Because we started at 10. And if the standard deviation is 3, one standard deviation away would be 10 plus 3, gives you 13. That would give you a z-score of 1. Another standard deviation away would give you 16. That would be a z-score of 2. Okay. Same thing if we're moving to the left. So that would be a value of 7. The data point would be 7. And because it's one standard deviation to the left, it would have a z-score of -1. Okay, the z-score simply is how many standard deviations away from the mean the data point you're referring to is. I'll say that again. The standard deviation, or sorry, the z-score is just how many standard deviations you are away from the mean. That's it. Okay. So we have a formula for calculating the z-score. You're going to be using this formula a lot, so you should become pretty familiar with it. So Z obviously is our Z score, and the way we get it is we take whatever data value we're looking at, because remember, every data point has a corresponding Z score. So we take the data point, from it we subtract the mean of the data, and then we divide it all by the standard deviation of the data. Okay? So if we use that formula, we can calculate the number of standard deviations that any data point is away from the mean, even if it lies between whole standard deviations. Okay, so this is kind of another similar diagram, right? It has your standard deviations there, and it has your Z scores there. Okay, so let's do an example. So for this one, it looks like we're studying the heights of a basketball team. So these are measured, or these heights are given in centimeters. So 170, 182, 193, 195, and 212. So we're given the mean and we're given the standard deviation, right? So we get the mean is 190 centimeters. We're given the standard deviation is 15 centimeters. Okay. Calculate the Z score to the nearest hundredth of the tallest and the shortest players. Okay, so those are two separate X values. So we'll do XS for shortest, and we'll do XT for tallest. So the height of the shortest player is right here, 170. So that's XS. And the height of the tallest player is right here, 212. So that's XT. Okay. So what we're going to do is we're going to find the Z score for both of them. So we'll do the Z score for the shortest player first. Okay. So if you take a look at our formula, Z is equal to X minus X bar divided by sigma. And of course, X is going to be XS in this case because we're taking a look at the shortest player. So all we have to do now is make our substitutions. Right, so in this case, XS is 170 centimeters. X bar is the average, which is 190 centimeters, and our standard deviation, of course, is 15. So in this case, we'll get a Z score. So 170 minus 190, of course, is negative 20 divided by 15. And of course, that reduces to negative 4 over 3. So that would give us a Z score if we rounded it off to the nearest hundredth. That would be a Z score of negative 1.33. And that's, of course, Z score of the shortest player. Okay? And that makes sense because we would expect a negative Z score for this player because we knew that the average height was 190 and this player's height was 170. So this player was shorter than the average. We would expect a negative Z score. Okay. So let's do the Z score for the tallest player now. And again, of course, we're going to be using the same formula here, but instead of using XS for the smallest, or for the shortest, we're going to use XT for the tallest. And of course, the average and the standard deviation stay the same. So in this example, 212 is the height of the tallest player. So, and the average is 190. So because his height is larger than the average, we would expect a positive Z score. So let's see if that works out to be the case. So again, we're just substituting our values in here. using red to show my substitution. So xt, as we got from the question, is 112 centimeters. The average height is 190, and again, the standard deviation is 15. Those two values are not going to change player to player. All right, so for this one, this is going to be 22 over 15. So if you get your calculator out here and round this one to the nearest hundredth, you'll get a value of positive 1.47. Okay, so those would be the corresponding z-scores. So the value of the 170 centimeter player was 170, obviously, but the corresponding z-score to the 170 data point is negative 1.33, and the corresponding z-score to the data point of 212 is 1.47. Okay, so both of those points have their own corresponding z-score. Okay, but why do we care? Why do we care about these z-scores? What do we use them for? Well, I'll show you in the next example. Okay, this is kind of a classic question for this kind of problem. So next example, Tony's marks on his midterms are shown below with some relevant data from his classes. Determine which test he performed better on compared to the rest of the class. That's the important distinction here. So we have math, we have physics, we have English, we got Tony's mark, then we also got the class average, the mean mark, and we also got the standard deviation of that class's grades for that midterm. So we can't just take a look at Tony's mark and say, oh, he did better in physics because he got a 79. That was his highest mark out of all of his classes, right? So he did the best, that was his best mark, but we don't know if that was the best compared to the rest of his class, because although Tony got a 79 on his individual physics test, and that's his highest test, we can see here that the class average was also the highest in physics. So Tony did well in physics, but the rest of his class also did better in physics as well. So essentially what we're asking here is if we have our standard curve, right? Actually, maybe I'll draw it this way. It's probably better if I draw it this way. I'll make it really big. So this would be like a mark of 0, and this would be a mark of 100. Assuming all of these classes have evenly distributed marks, right? His English class could be here, right? His physics class could be here, and his English class could be like here, for example, right? They could be anywhere on this line, and what we're actually asking is out of each of those curves, which one did Tony get the farthest to the right? Did he get it there? Did he get it there? Did he get it there? Right? The farther to the right he is, the more standard deviations away to the right from the mean he is, the better he did than the rest of his classmates, which would be over here. Okay, so we want to find the class that Tony had where he scored the most to the right, because that means he would have done better than most of his classmates. And well, what tells us how far we are away from the mean? Well, that's the z-score, right? That tells us how many standard deviations away from the mean Tony is. So the highest z-score out of those three classes is going to tell us how he did compared to his classmates. okay? Because we're not just looking at how well he did with just his raw data. We want to see where he is compared to the rest of his class. Okay, so we're looking for the highest z-score here. Okay, so let's do z-score for math. So that's going to be his mark for math minus the class average from math divided by the standard deviation of the marks from math. Okay, so his mark for math was 74. His average, the class average there was 68, so that's good. He beat the class average, so he's going to get a positive z-score. And the standard deviation was 12. Okay, so what's that going to be? So it's going to be 6 divided by 12, which of course gives us a z-score for the math class of 0.5. Okay, so that doesn't tell us anything on its own. That number is useless on its own. We need to be able to compare that number to the other classes. Okay, so that was for math. We'll do the next one for physics. ZP. So for this one, we're going to take his mark from physics, subtract the average score of the exam from physics, and divide it by the standard deviation of the physics exam. So his mark here was 79. The class average for physics was 73. And the standard deviation was 14. So take a look here now. The standard deviation from the math class was 12, and the standard deviation from the physics class was 14. So we know, because physics had a higher standard deviation, that the marks were more spread out for the physics exam, right? Okay, so what do we have here? 79 minus 73. That's going to be, what is that going to be? It's going to be 6, right? Divided by 14, which is 3/7, which gives us a z-score for physics equal to about 0.43. All right, so right away we can see that Tony did better than most of his class on the math exam, more so than the physics exam. There were more students in front of him on the physics exam than there was on the math exam. So far he's done better on his math exam. So let's take a look at English. So he scored a 68, and the average was 66. So he only did 2% better on the average. But the standard deviation is the smallest for English. It's 11. So although he didn't score too much higher than the average on his English exam, because the standard deviation is smaller, that means smaller and smaller differences in his percentage will give him a higher z-score compared to the other classes. But let's do the calculation and let's see how it works out. So we'll take his English mark, subtract the class average from the English exam, divided by the standard deviation of the English exam. So his mark is a 68 minus 66 divided by 11. So it's going to be 2/11, which is going to give him a z-score for English. 2 divided by 11, that gives us about 0.18. Okay, so the highest z-score here is his math test. He did the worst on his English exam, and that was also the course where he did the worst compared to his other classmates. So he got, if we were going to try to think of the standard curve here, this would have been his English, something like that. This would have been his physics, and then this would have been his math. He would have scored more so to the right on his math exam. Okay, so we'll say, therefore, what's this guy's name? Tony? Did better than most of his class on his math exam. Right? Because although he got a higher absolute mark on his physics exam, a 79, because the class average was higher, that actually didn't work out to be the course where he did better than most of his classmates. He did better than most of his classmates on the math exam. Okay, so that's one way we can use z-scores in real life. Anyway, hope you guys are staying safe out there, taking care of yourselves. That's going to be all for this week. So at this point, you can go ahead, work through the rest of the questions in the workbook there. So that's going to be page page 271. So I asked you guys to just do questions 1 and 2 last time. You can work now through 3 to 12, and make sure you hop in the Discord and post any questions there you might have. All right, guys, stay safe, and I'll see you next week. Bye.